Hello, everybody. My name is Lekshmi Santhosh, and here I will be going through the details of my final project, which is TensorFlow and neural networks for music recognition. So, in this project, I attempt to identify the most predominant instrument that was used in a musical composition using convolutional neural networks. The implementation of this project is done in TensorFlow. Since it is pretty computationally intensive, I decided to use Google Cloud Platform. The entire project was done on a single node, which has 8 cores and 12 gigabytes of memory, and I used a Linux virtual machine for that. And I deliberately chose a cloud computing platform so that we can, in the future, for expanding this project, we can very easily do so on the cloud. In addition to that, Python libraries were used for visualization for intermediate calculations and transformations, and Jupyter Notebook was also used to organize the details. Now let's quickly look at the high-level solution overview. As I've mentioned, the input layer to me are 3-second musical recordings in .wav format. This was converted to a spectrogram for ease of processing and then passed through a 5-tier convolutional network for learning. And the outcomes were discretized into 4 specific classes using a softmax classifier. Now let's look into the details of each tier. IRMAS was a public database that was available with all the recordings curated as 3 seconds. It's publicly available. The data is very clearly labeled and organized in folders. Now the only downside of this data set was it was not programmatically accessible through Python. So what I ended up doing was manually downloaded it to my local machine, and I had to upload it back to the cloud instance, which was pretty time consuming. And the second challenge which it posed was there were more than 12 different classes of instruments, and the data set was highly skewed. In other words, some instruments had way less observations than the others. So I, for ease of computation, ended up choosing the 4 most predominant instruments in this data set, and that was used as our source. And as I mentioned in the introduction, we cannot use a raw music file for processing or for learning. So we had to convert that into a spectrogram, which is a representation of the frequency variations over time. It can be imagined as a photograph of a song. And also, this spectrogram was additionally processed to rescale it to the MEL frequency, which is the frequency at which humans perceive sound. So we are trying to simulate human hearing as much as possible in the pre-processing stage. Now, once we have those spectrograms ready, it is all set to be passed to our 5-tier neural network, convolutional neural network, which has 4 convolutional layers and 1 fully connected layer. Now, in all 4, the design for all the 4 convolutional layers are very similar. The first layer, however, does not have dropout, and in the subsequent slide, I'll explain why I have made the design decision to do a dropout. Now, all the 4 layers use a 3x3 convolutional filter, followed by an activation function and max pooling for dimensionality reduction. Now, the linear rectified linear unit was used as a linear activation function, and there was a reason why I chose a nonlinear activation function, because if I had chosen a linear activation function, the output would have been a mere linear representation of the input alongside the weights and the bias estimates, which is not really what we wanted, because very rarely is reality a linear representation of parameters. So by adding this linear nonlinear function in here, we account for the nonlinearity, and thereby we reduce the bias of the model. Max pooling was the pooling that was used to reduce the dimensionality, or to reduce the number of parameters that are being passed to the subsequent layers. Now, convolutional neural networks learn through a technique called backpropagation. What that means is, when it is presented with the training data for the first time, it has no clue how to estimate the weights or the bias. So what it does is, it starts with a random guess, propagates that estimates all throughout the 4 layers, arrive at making a probability prediction, and then it evaluates how well it has predicted by comparing the predictions with the truth, which is a class label here. So this is the ground truth. And then, based on the evaluation, the loss is passed to an optimizer function, whose job is to find out the most optimized parameter for which we have minimal loss. So based on the optimizer inference, the parameters are adjusted, and that process is called backpropagation. The modified parameters are given back to the model, which again relearns the spectrograms with the updated parameters, and this process continues till the loss is minimized to a number close to 0. This is an iterative process. Now, one of the challenges that we have with backpropagation is it constantly changes the weights, and that inadvertently induces an internal variance in the data set. So to make your model stable to this changing parameters, batch normalization can be applied. So in batch normalization, each mini batch that arrives, when I say mini batch, it's a random sample of the spectrogram from your training data, is taken, its mean and variance is computed, and then it is re-standardized or rescaled to have 0 mean and 1 variance. So by doing batch normalization, the covariance is controlled by a great extent, and that improves the model performance by a great deal. So that was one of the design decisions that I made in this project. And another modification which was done, or another key parameter that was done, was dropouts, as I've mentioned in the previous slide. In dropout, what we do is, in each of the hidden layers, a certain percentage of networks are randomly dropped or removed from learning. And this process is highly randomized, and this deliberately adds noise to your prediction, thereby making it more robust. And again, as I've mentioned in the overview slide, we use softmax classifier to discretize, to identify the probabilities of each of the 4 classes, and Atom Optimizer is used in this project to identify the optimal parameters. The results slide. Unfortunately, I could not attain a great accuracy with this design, and based on my preliminary diagnosis, it has everything to do with the small data, the trained data size that I had. So I used only 2,000 recordings for training this model, and a large part of it attributed to the difficulty in programmatically accessing this data directly from the website, and um, also I could not leverage the test data set that was already curated from this database, because the test had multiple labels assigned to the same music. So I wanted to, as the first phase of this project, I wanted to keep this simple, and hence I decided to uh, take a percentage of the training for validation, and that again reduced the number of examples I had for training. So lack of data is, I consider lack of data to be one of the primary reasons why the accuracy is pretty low. However, it is interesting to see how the loss, which is this chart on the right, tends to minimize after several realizations, and tails down around zero. Challenges. As I've mentioned, data extraction was one of the key challenges that I faced, and due to that, I ended up making a trade-off in the volume of data with which I did the training, and that took a toll on my model performance. And another challenge which I faced was TensorBoard, for some weird reason, did not work on my VM instance. So what I ended up doing was I created the graphs and exported it to my local machine, and captured the screen prints and the graph screenshots from my local machine. So that was another challenge that I faced. Next steps. There are a lot of opportunities for improvement in this work. So the first thing, as I've mentioned, is gather more data. Again, based on the research that I've done, there are other databases such as the MedleyDB, which has more musical clippings. Now the challenge about this is the data set in these databases requires significant pre-processing. We will have to programmatically eliminate silence from these recordings. And the second thing, which I definitely want to do, is evaluate the quality of the clippings that are housed in these databases. Whatever data that I used for training was randomly sampled for quality, and some of them were good, some of them were okay, some of them had a lot of static noise in the background. So we can again use RMSE function or RMS functions to evaluate the quality of signal within a clipping and set a threshold. And again, since I was facing a starvation for training data, I ended up not implementing any data quality checks, and I used whatever I had. Hyperparameter tuning is also something which I definitely want to invest in by using iterative methods. I want to identify the best hyperparameter for which the model performs the most. Now, the fourth improvement which I want to make is batch normalization for testing. So currently I'm using the test parameters for making for batch normalization. Ideally, we should be estimating, since test data is unseen, is purely unseen, and to prevent any leakage of test information during the training phase, you have to estimate that the mean and the variance from the mini batches during the test phase itself. So that's something which I want to try as a next step. And then eventually, once I have a lot more data, it obviously requires more computation, and then I would definitely want to implement this model in a distributed computing environment across using multiple train nodes and running TensorFlow in a distributed environment. And that's it. Thank you, everyone. Bye-bye.